I am Derek Allen, and I, together with Blake Fullenwider, performed an experiment in an attempt to develop free convection Nusselt correlations for cylinders at an angle. Currently, we only have Nusselt correlations for vertical or horizontal pipe, but not for pipe set at an angle. The basic idea of this project was to experimentally determine H values that we could then compare to the theoretical values obtained from our known vertical and horizontal Nusselt correlations. If we are able to accurately predict the H value in our experiment, then the experimental H values obtained at our other chosen angles will be used to develop some Nusselt correlations based on a curve fit. To experimentally determine our H value, we first selected a PVC pipe, which we then filled with ice water. Because we know that liquid undergoing a phase change is at a constant temperature, this will allow us to achieve steady state conditions. An assumption that we made is that the surface in direct contact with the water at steady state conditions is equal to that of the water. Zooming in on the wall of the pipe, we can use the resistance method from the inner surface of the pipe to the outer surface of the pipe, and from the outer surface of the pipe to the surrounding air, where each node represents the temperature at that given point. We stated that the energy transfer rate from the inside surface to the outer surface of the pipe is the same as the energy transfer rate from the inside surface to the air. The heat transfer from the inner surface to the air, consisting of conduction and convection, is as shown. The heat transfer from the inner surface to the outer surface, or just conduction, can be replaced by this. With this equation, we can then solve for H, which gives us this. Using thermocouples, we can obtain all of our temperature values. We know the inner and outer radii, and K is a material property. Now it's just a matter of gathering the data. The experiment we used consisted of hanging the pipe filled with ice water by these two strings. This string was later slid down to the far end so the pipe could pivot about this point by lifting up on this end and setting it at our desired angle. 3 locations were selected and labeled as bottom, center, and top. At each location, 3 thermocouples were used, one at the top, one at the middle, and one at the bottom. This was necessary because a pipe undergoing free convection experiences uneven heat transfer rates. In our case, the center has the highest heat transfer and will therefore be at the highest temperature. The top is in the mid-range of the heat transfer, and the bottom is the lowest. For this reason, we took multiple measurements and averaged them. Water and ice were added here. A thermocouple was also placed in the hole to measure the water's temperature, and a rubber stop was inserted. The angles we took measurements at were 0 degrees, 30 degrees, 60 degrees, and 90 degrees, or vertical. Each angle was verified with the angle gauge that was seen in the previous slide. At each angle, we waited until steady state was achieved and then recorded the temperatures. With our average temperatures, we calculated the H values for each angle and each position along the pipe. After some analysis, we discovered that our vertical or 90-degree test data was unusable, which will be discussed in a later slide. So we compared our 0-degree measurements to our theoretical values to determine if, from our data, a Nusselt correlation can be approximated. To get our theoretical H values, we calculated our Grashof number, then our Rayleigh number, and using these two values, we found the Nusselt, and ultimately our H values. Significantly, our theoretical values ended up being significantly different than what was determined experimentally. Because of this, no Nusselt correlations of any value can be determined from the data we gathered. So the next approach would be to analyze some potential things that could have caused the inaccurate data. Some of these possibilities could be due to the assumption we made, not fully understanding the limitations to the equations we had intended to use, and neglecting some potentially significant aspects of heat transfer. If you recall, we made the assumption that the inner surface temperature is equal to that of the water. That assumption is only good and safe when resistance within the water is much less than the resistance through the wall. To avoid this, thermocouples could have been placed on the inside of the cylinder, or the water resistance could have been calculated and determined if it was insignificant. The equation that we have for the vertical plate can be used for a vertical cylinder so long as this ratio holds true, an important limitation we neglected to plan for while designing our experiment. Our diameter over length ratio came out to be approximately 0.03, while the 35 over Grashof ratio was about 0.2, which clearly makes this statement false. So why is this limitation so important? If you look at a vertical cylinder, free convection will form a laminar boundary layer so long as the D to L ratio is large enough. Once the length becomes much larger than the diameter, the boundary layer will transition to turbulent. The vertical equation that we have does not account for any turbulence, making our theoretical H values different than what we would actually see. One aspect of heat transfer that was neglected altogether was that of radiation. The radiation would be occurring between the outer surface and the surroundings. Although the experimental values are incorrect, there is a trend worth mentioning. For the vertical case, and potentially the angled cases, we decided that it was likely that the boundary layer at some point along the length of the cylinder turned from laminar to turbulent. If we plot h as a function of x, or the length of the pipe, as long as the boundary layer is laminar, h would decrease like this. But once the boundary layer changes to turbulent, the h suddenly increases and then continues to drop off. It is possible that the selected location for the thermocouple landed in locations such as these. This could explain why our experimental h's are lower in the middle and higher on the ends. This explanation, however, fails to explain why the h value is lower in the middle for the horizontal case, which should have all been equal. To wrap things up, although our experiment did not lead to the development of a Nusselt correlation for angled pipe, some important keys were learned regarding free convection and experiment setup. If we were to perform this experiment again, we would first verify any assumptions by performing any needed calculations, or gather any extra data and determine any limitations to the equations being used and ensure our tests fall within them. Thank you for watching our video, and we hope you learned something new about free convection.